Hi everyone. Now we're going to start chapter 6. And up until this point, everything that we have been doing falls under the realm of descriptive statistics. At the very beginning of this course, we talked about there being two types of statistics. There was descriptive, which was just calculating things or describing things about a data set. And then there's inferential statistics, which is the whole analyzing the data using sample statistics to make inferences about populations. So that is where we're going to start with chapter 6. We are going to be calculating something called a point estimate. And used to determine information about a population parameter based on sample statistics. Because let's face it, the reality is we will not be able to calculate population parameters like the true average or the true proportion that something happens very rarely, because very rarely will we be able to obtain all of the population information to be able to calculate those. So what we do is we calculate a point estimate, which will be a sample statistic that we can then use to make an inference about that population parameter. So examples of point estimates would be using X bar, which is sample mean, to draw a conclusion about mu, which is population mean. Another example would be using S, which is sample standard deviation, to draw a conclusion about sigma, which is your population standard deviation. And then the third example would be using what we're going to call P hat, not fat, but P hat, which is sample proportion, to draw a conclusion about P, which is population proportion. So when we talk about point estimates, or when I use the term point estimate, hopefully that will give you a little bit of information as to what I'm referring to. The big thing is that we will not be able to estimate a population parameter down to the exact value, because using a sample to estimate a population parameter, there's still going to be error involved. They're not always, just like you saw with the sampling distribution of X bar, there's going to be a range of values that that population mean could be based on the fact that there's a range of values that the sample mean can take on. So what we're going to be doing, instead of trying to estimate a population parameter exactly, we're going to be creating something called a confidence interval. And a confidence interval is an interval created based on a point estimate and a given level of confidence that estimates the range that a population parameter should fall in. So this confidence interval will start with a point estimate. That's going to be your center. So because that's in the center, we're going to need to go above the point estimate and below the point estimate to create that interval. So we'll take the point estimate and we will both add and subtract a critical value times the standard error of the point estimate. The critical value tells you how many standard deviations of the sample statistic to go out to achieve a specific level of confidence. So the critical value is attached to the confidence level. And since I stated that it's the number of standard deviations, we have a term that is defined by the number of standard deviations. And that will become a specific designated z-score. So z sub c is going to be the z-score associated with a specific confidence level. So I'm going to show you how to do this by hand, but then there are also charts that will give you these specific z-scores that you'll need to use if they're the common ones that are used every time. But let me kind of explain what it is. So if I were to look at the normal curve, and this is going to go back to section 5.3 from the last chapter. And I want to look at where 90% of the data would fall. I could use this to associate with a 90% confidence level. Now what you will see is we will most often use 90%, 95%, and 99%. It doesn't make a whole lot of sense to just be 70% confident something will happen. We want to create these intervals with enough validity that the likelihood that it doesn't happen gets smaller and smaller. So, like I said, we're going to focus on 90%, 95%, and 99% most of the time. But I'm going to show you how to calculate this so that if you have a problem that asks you for any different confidence level critical value and you don't have that in your chart, you can easily calculate it by understanding what it is you're calculating. So basically what I want to look for is the negative z-score and the positive z-score associated with 90% of the data being between them. Well, if that's the case, if 90% is in between, then that means 10% is left on the outside. And since this is symmetrical, that would mean 0.05 is on this side and 0.05 is on that side. So if you remember from section 5.3, what we used to get the z-score associated with a probability, we did inverse norm. We did the probability to the left of the line. So in this case, it would be 0.05. We're looking for a z-score, so that would be a mean of 0 and a standard deviation of 1. So if we go to the calculator and we use second vars, 3, and the area is 0.05, the mean is 0, the standard deviation is 1, then we get negative 1.645. So that means that the z-score on the negative end is negative 1.645. And I could also do inverse norm of 0.95, which would give me the probability to the left of this line right here, 0 and 1. So second vars, 3, 0.95, 0 and 1. And you can see it's positive 1.645, which hopefully makes sense to you because, like I said, it is symmetric. So you really only need to find one end because we're looking at both the positive and negative z-scores that are associated with 90% being in between them. So that kind of takes you through how I would find a z-score. And I told you that the common ones we were going to use were 90, 95, and 99. So I'm going to go ahead and do those for you. So the negative z-score and the positive z-score associated with 95% being in between. So I would do inverse norm. This time, if 95% is in between, then that means 0.05 is outside, and divide that by 2, and you get 0.025. So I'm going to inverse norm 0.025, 0, 1. .025. And I get negative 1.96. So again, with the concept of this being both the positive and the negative, on the right-hand side would be positive 1.96. And then for the last one, if I did the negative and positive z-scores associated with 99% of the data being between, then that's 1% on the outside. Divide that by 2 because I have 2 tails that have to accommodate all of that 1%. So when I divide that by 2, I get 0.005. So second var's 3. 0.005. And I get negative 2.576. So that would be negative 2.576 and positive 2.576. So the first thing that I want to kind of point out with all of this is that for specific critical values that are attached to confidence levels, oops. Notice that when we did 90% confidence, our z-score was positive and negative, or excuse me, our critical value, because positive and negative is part of the formula, our critical value was 1.645. When it was 95%, whoops, sorry about that, our critical value was 1.96, and when it was 99%, our critical value was 2.576. And these are going to be common Z sub C or critical z-scores for these 3 specific confidence levels that will be used over and over again. So let's go back to the confidence interval formula. Remember, I said that we were going to do point estimate plus or minus critical value. And I've just shown you how to find the critical value times the standard deviation of the point estimate. This part of the confidence interval is called the sampling error. This part, the standard deviation of the point estimate, is called the standard error. So just for vocabulary purposes, the amount that we're going to go away from the point estimate is the sampling error. In other words, how much error is involved based on a specific level of confidence, because this is a sample that we're basing everything on and not the whole population. In section 6.1, the type of confidence intervals that we're going to calculate are for the mean. So we're going to look at the confidence interval for the mean. And if you go back to section 5.4, using X bar as my point estimate and Z sub C as my critical value, section 5.4, you'll remember the standard deviation of X bar was sigma of X divided by the square root of N. So that's what I would do to calculate a confidence interval. I would have to know 3 things: the sample mean, the population standard deviation, actually 4 things, the sample size, and the confidence level. So those are things that you would have to be given to be able to calculate this confidence interval. So let me kind of show you what would happen here, because I'm sure all of this is very unfamiliar territory and probably doesn't make a whole lot of sense until we actually put it into play. So we're going to look at an example. A sample of 64 freshmen from a university had an average GPA of 2.9 at the end of their first year. Estimate with 95% confidence what the true average GPA for freshmen at this university should be. Assume the population standard deviation is known to be 1.4. So I have an N, it's 64. I have a sigma, which is 1.4. I have an X bar, which is 2.9. And I have a confidence level of 95%. So my Z of 95%, based on my table from above, was 1.96. Or my Z sub C is 1.96. And again, that's based off of 95% confidence. And if you look back up here, for 95%, my Z score is 1.96. So if I fill in my formula, X bar plus or minus Z sub C times sigma over the square root of N, my X bar is 2.9 plus or minus 1.96 times 1.4 divided by the square root of 64. So that's 1.96 times 1.4 divided by the square root of 64. So 0.343. So what that tells you is that the the sampling error is 0.343. So that means I'm going to take the 2.9 and I'm going to add 3.3 and subtract 0.343. And that gives me 3.243 on the upper end. And then 2.557 on the lower end. So I have my point estimate in the middle. So the midpoint of this interval, if I gave you just an interval and asked you what the point estimate was, you would just average the two and get the middle point, which would be 2.9. And 2.9 plus 0.343 and 2.9 minus 0.343 gives you that my confidence interval is between 2.557 and 3.243. So if I wanted to interpret this, what is it that I actually found out? I would say I am 95% confident the true average GPA for freshmen at the end of their first year at this university is between 2.557 and 3.243. And that's how you would interpret the confidence interval. So that goes through showing you how the interval is created, what each of the elements of the interval are, and then back up here why we're actually doing this. Because we cannot determine a specific exact value of a population parameter, so therefore we create an interval based off of a sample statistic that gives, using sampling error, where we can be confident that the true population parameter would fall. And that's the end of section 6.1.